Hello students and others finding this video. I'm Dr. Ryan Hayes at Andrews University, part of the chemistry department. Thank you for joining me. We're going to start talking about nuclear chemical reactions and how does a chemist look at these things. Kind of get us started, I always like to have a question here. Is cesium-133 heavier or lighter than the average atomic mass for all naturally occurring cesium isotopes? What do you think, heavier or lighter? Or are they exactly the same? What do you think? Are you sure? I mean, how do you even think about this? So I like this question because it digs up some things to see if students understand. Like, how do you know what the average atomic mass is for all naturally occurring cesium isotopes? One way you can know this is by, looking at the periodic table. Remember that the mass that you see is on the periodic table is the average, weighted average of all the isotopes of cesium. So then how does cesium-137 compare? All right, hopefully you've waged your answer. So we're gonna report and that it's heavier. 137, definitely bigger than 132.9. So that isotope is heavier. We're gonna use this thinking to make some decisions about the nuclear chemical properties coming up. So let's jump into that. I call this my lecture 60 for the year, for the semester actually, in our Chem 132 series. And chapter 18 out of the Zumdahl textbook, An Atom's First Approach. Here we're going to be looking at a couple of different items here. Here are subtitles, subtopics: nuclear stability and radioactive decay. What is it? What are the kinetics of that? It has to do with radiometric dating and how long isotopes live and how we can predict that and calculate. What are some nuclear transformations and uses of radioactivity? And then we'll talk about some of the power behind these things. And I hope one of the things we can kind of learn out of this chapter is what's the purpose of radioactive elements in the Earth? Why would we have these things? And what can we use them for? Certainly some of the uses, just to kind of lay it out there, are for medical purposes. Radioactive isotopes are very important in medicine. One of them is to use as tracers, to go and localize in various organs or tissues to help visualize the blood, pathogens, cancer, different things, very important, or even to treat different ailments. Nuclear chemistry is very important in the medical field. Secondly, nuclear chemistry is a very critical component to the power consumption and power production for the world. And it's more important, less important, depending on what country you're in. And there's a lot of issues associated with that. We actually have one, we have a nuclear power plant not too far from here. I was able to visit a few years back, the Cook Nuclear Power Plant. And this is located in Bridgman, just 11 miles south of St. Joe on Lake Michigan, not too far from Bering Springs, Michigan, where we're located. And one of the other big topics that comes into this chapter that we can think about is radiometric dating. How can we use radioactive materials to find the age materials? What are some of the theories behind that? Talk about that. All right, to get started, a little bit of review. This takes us all the way back to the very beginning of general chemistry and understanding how we use the symbols and where we write numbers. I would say we'd spend the last few chapters focusing on the subscript most of the year, subscript to the bottom right, and the superscript for the charge in the upper right. Go to top left. What's that one's for? A. What does that represent? What do you think? And what do you think Z represents? Atomic number, atomic mass, neutrons, protons, electrons, something. What do you think? All right. Answers? Okay, A represents the atomic mass. So like when we said cesium-137, you could write a 137 in there for the atomic mass. What's Z? Well, hopefully you guessed atomic number. Notice I left out protons. It's actually the number of protons, which gives the element its identity, its properties, its function. Okay, so Z also represents the nuclear charge in some ways. Okay, so we want to think about that. And you'll see that with some other small subatomic particles like the neutron, proton, electrons. So pay attention to what we see down there in terms of that number, okay? All right, so now we know that A is the mass number. Where does that come from? It comes from the sum total of the protons plus neutrons. Z really is the number of protons. So if we needed to figure out the number of neutrons, we could just subtract those two numbers there. Boron 10, that is the way we would say it, dash A. It really is the number there. We can put that 10 behind the name or upper left superscript there for the symbol. 5 protons and 5 neutrons in an isotope of boron 10 is boron 11. Same number of protons, because that's makes it boron, and it makes this particular version an isotope because it has 6 neutrons, total atomic mass of 11. So what's changing is the mass, which comes from properties on the inside. Boron 10, boron 11, a lot of the same electrical properties. It will form the same ions and the same type of compounds, and you can't really tell until you do some kind of analysis to figure that out. The term nuclide is something that we would use as a generic term for isotope. So you'll hear nuclide or isotope. And we'll refer to the subatomic particles as, especially those that are in the nucleus, as nucleons. So it's just a general generic term for proton and neutron. So instead of just saying proton and neutron, we'll just say, hey, the nucleons. All right, there's a nice little video to kind of introduce what is radioactivity and how do we think about it and some of the issues or particles actually that come out of that. Hopefully this video will work.
At the end of the 1800s, physicists were staggered to find there was radiation coming out of all kinds of things, just dirt and rocks. The very first time this was discovered was with a jar of uranium salts that was left in a drawer overnight, and in the morning, a photographic plate that was next to it had been exposed, even though it had been in the dark all night. So where had the radiation came from? From this stuff, uranium salt it was. So to discover that dirt was giving out radiation, there was worse in store. They discovered that there were 3 different types of radiation going on. So they really had no idea what was happening. So what do as a scientist? You name it. So they named it A radiation, B radiation, C radiation. Well, that's a bit dull really, isn't it? So maybe let's go for something more sciencey. Alpha, beta, gamma. Yeah, that's much better. And I've got an example here. I've got some alpha, beta and gamma radiation, gamma sources here. I also have a Geiger counter, which is a little device that gives off a click when it detects radiation. So I can hold it over the source. You can hear you get a lot of clicks. So what are the different types? So our alpha, it turned out, pretty much completely blocked by paper, whereas the beta and the gamma makes basically no difference. So if we try lead, our alphas are completely blocked. Strontium, the beta is pretty much blocked, but our gamma source, it makes basically no difference. So we can even go to a thick, solid piece of lead. And you can still see some things are getting through there. So we could try. There's a bit penetrating through. But I think I must be thicker than lead. So what are our 3 types of radiation? Scientists eventually worked out that the alpha radiation is matter, so it's 2 protons, 2 neutrons. That's the nucleus of helium. The beta source gives out electrons, and the gamma source gives out electromagnetic radiation.
All right, great little video. Nice channel, veritasium.com. Encourage you to
At the end of the
subscribe. All right, alpha particles, helium atoms coming out, beta particles, electrons, gamma radiation. It's important to start having a visual conceptual understanding of what these are. So gamma radiation, this is a version of light, very dangerous version, very high energy part. So the others, alpha, beta, these are particles that come shooting out of radioactive materials. Gamma radiation, think of it as light. What kind of things does light do? For the others, think about particles. If you shoot particles at something, what does it do? If you shoot light at something, it's going to behave differently. There are 83, we would say, stable elements of the bismuth, and then starting at polonium number 84, that's a good number to remember. At polonium and higher, all of these elements, all of their isotopes are radioactive. They are decaying. They are giving off these particles. They're just unstable, and they're spewing forth protons, protons in the form of alpha particles and beta particles and gamma radiation. These three things are just shooting out of these elements. Now, there are radioactive versions, radioactive isotopes of some of the other elements below 84, but there's a sort of a switch over at 84 that we need to be aware of. All right, what is the symbol for a neutron? What do you think? So we've just kind of reviewing this A and Z and what do you know? What do you remember? All right, hopefully you picked A. Why would we pick A? Well, remember that atomic mass is the number on the top left. So that superscript on the left tells us its mass. So the neutron has a mass of 1. And so remember, Z, the subscript on the left-hand side, tells us something about its charge. The neutron has no charge, so that's why it's a 0. Good. So those are some good things that I would say the symbol E represents a proton. The other ones are distractors. So this radioactive decay is something that's just happening to these elements. And there's some theories and explanations why. It's not part of this class to know why, but we can start to learn something about the relative stability of the elements on the periodic table. 279 out of 2,000 known nuclides are stable. That means there are more that are unstable than stable. There are more that are radioactive than are not radioactive. Some elements are very stable, including all of their isotopes, like 10, which has 10. As I've already mentioned, by looking at that periodic table, that nuclides with 84 or more protons are unstable, starting at polonium, an element that Marie Curie discovered. Light nuclides are stable, especially when they're Z equals A, which means you have about the same number of neutrons and protons. There's something unstable when you start having more neutrons and protons. For heavier elements, though, this neutron to proton ratio required for stability actually becomes greater than 1, meaning it's okay to have some more neutrons versus protons. And once again, why is not something we're going to spend time talking about, but just rather observing some trends in behaviors. Certain combinations of protons and neutrons seem to confer special stability, kind of like what we see with electrons in various elements. Even numbers of protons and neutrons seem to be more stable. So out of that 279 nuclides that we were talking about, isotopes that were stable, 168 of them have both an even number of protons and an even number of neutrons. Some examples are given there, like carbon-12 and oxygen-16. And then you can see that an even number of protons or just an even number of neutrons seem to confer some stability. And it's rare to have a stable isotope with odd numbers, but not impossible. Right, 279 is the total if you add those up. Certain number of protons seem to confer some stability. Numbers 2, 8, 20, 28, 50, 82, and 126 seem to be relatively stable number of protons. Just like there was stable numbers of electrons, if you think back to the noble gas configurations. All right, and then you can see the numbers there, 2, 10, 18, 36, 54, and 86 are the noble gas numbers, protons, the atomic numbers there. If one was to plot the number of protons that an element has versus its number of neutrons, the 45-degree angled line that's coming up there, you would see that a lot of the lighter isotopes are on that line. That's the line of stability, or at least the line of 1-to-1 neutron to proton ratios. The red colored little dots are actually where we find the stable elements. And so they veer off of this 1-to-1 proton to neutron ratio. and or neutron to proton. And you can see that they go up to a certain point and they stop when they get to 84. The blue dots are the unstable isotopes. You can see there are a lot of them, and they surround both high and low from this ratio. So this is an interesting graph, and we'll come back to it. All right, there's the different types of radiation, alpha. And one way you'll see this is as it's being emitted. That means we'll write it as a product. And we're going to start to see and understand how to balance and write nuclear chemical reactions. And it's important to note that we will always conserve the number of nucleons, and both as the mass and atomic number. So if uranium-238 gives off a helium, then it is left over with an atomic mass of 234, and the atomic number goes down by 2, and that's thorium. All right, beta emission. If you give off an electron, what happens? Well, this electron is not your normal electron. This is not something that will change the charge. This is what we normally assume. This electron is actually something that's emitted out of the nucleus. And so we're going to use the 0, -1 symbology there for our electron. And what actually happens there is a neutron gives off an electron and converts into a proton. That changes the identity of the element. And so you can see that the mass number and the atomic numbers are identical in this thorium-234 reaction, that both sides add up to 234 for their masses, and both atomic numbers add up to 90 on both sides, because 91 plus a -1 equals 90. So once again, how does this happen? There's an unstable neutron that converts into electron and a proton, and the electron comes ejecting out of the nucleus, not out of the electron cloud that surrounds that. You'll often hear beta emission and electrons emission used interchangeably along with emission or production. We want to be ready for a couple different ways of saying things. Gamma rays can come out. They are light. They're photons. They have no charge and no mass. So they are written with 0, 0 next to them. And you'll have no idea on how many will come out of a chemical reaction or not. And so this information will typically have to be given to you. And you can see this is this exact same uranium-238 reaction that I wrote before in discussing the alpha helium particle that came off. But it turns out there is energy in the form of gamma radiation that comes off. So we need to know about that. A couple other new particles, or a couple of things to introduce to you. A new one here is a positron. A positron is an electron that comes ejecting out of the nucleus. It has a very similar description as the electron, 0 mass, but a +1 charge. And so here is a chemical reaction showing the sodium isotope, sodium-22, undergoing a change of nuclear chemical proportions by giving off an electron. So positron emission, that's new to a lot of students. Make sure you kind of get familiar with that. Now there's electron capture. An electron can be captured by the nucleus, something maybe that was in an inner s orbital, close, and if the conditions are right, an electron is captured by the element, the nucleus, and it converts a neutron into an electron and a proton actually combine to form a neutron. So the overall mass will stay the same, mercury 201 going to gold 201, but you'll see that the atomic number has changed because the number of protons have changed. So you want to be familiar with electron capture as a radioactive decay mechanism. This process also gives off a gamma radiation. How many? Once again, gamma radiation, you'll have to be told how many and if that's there. Electron and proton combine to form a neutron in the nucleus. Those are the main type that we're going to focus on. There's certainly others, but those are the main ones. Nuclear transformations are chemical reactions that involve nuclear chemistry, and we'll keep track of both the atomic number and the mass numbers here. And you can have things that bombard or run into each other and cause a chemical reaction, nuclear chemical reaction, to create other elements. And in those cases, oftentimes neutrons are given off. So they'll end up changing the mass of the element that's formed, but you will see that on both sides there is a balance in the mass number and in the charge, nuclear charge. Here's Californium 249 reacting with oxygen 18 to create seaborgium and 4 neutrons. And we have to keep track of the stoichiometry. When there's 4 neutrons, that means I have 4 times the number 1, and add that to the 263, and that creates on the product side let's see, for 267 mass units on the product side, and you'll see that there's 267 on the californium side as well. So we want to be able to recognize nuclear chemical reactions. All right, something to think about. We were able to show, and this picture is to reiterate it, that alpha particles, they're stopped by a little piece of paper. Beta particles can go further here through that, and gamma radiation even farther. So which one radiation penetrates the farthest? Alpha, beta, or gamma? Well, you can see here, gamma is the one that penetrates the farthest. Now, one of the questions I want students to be thinking about is which one causes the most damage? So we'll be thinking about that. I won't answer that one quite yet, but be thinking about that. All right, now looking at these chemical reactions here, which of the following produces a beta particle? A, B, C, D, what do you think? All right, you can always pause the video if you need some more time, but hopefully you'll notice that it was D that gives off a beta particle. A is an electron capture process, B is a positron emission, and C an alpha particle emission. Let's go back to this band of stability and radioactive decay, where there's some important things we can learn about what happens when we think about transformations, nuclear transformations, relative to this band of stability here. One of the ways we're going to look at it here is, here's americium-243 decaying by alpha particle emission to create neptunium. I believe that is the particle. And get my next slide to come up here. And that one has an alpha emission. So that's important to know. Typically, the things that are higher in mass will typically give off alpha particles. Now, beta emission tends to happen and beta capture tends to happen for lighter molecular or atomic weight elements and isotopes. So here is a beta emission, and what it serves to do, especially the all of these things, they change what's called the proton to neutron ratio. And that's important because things that are unstable are outside of a certain ratio, and by giving off or taking in something, you can get closer to this island of stability. That's the driving force, perhaps, in some of these chemical reactions, nuclear chemical reactions. So isotopes that have a low N to Z ratio that are, so basically they're in this graph, the red dots, they're below the band of stability. They are going to have a predictable decay either by positron emission or electron capture. It turns out these two things do the same thing, as I'll illustrate with this example with gallium-67. It can give off a positron to form zinc-67. Gallium-67 can also do a electron or beta capture and also form zinc-67. So how are you supposed to know? You can't know. You can just pick one. But here, how did we know that these things will decay in this way? So we're going to now learn how to predict whether something is going to predictably emit what type of particle. All right. These are important because elements want to continue to decay. These radioactive elements will continue to decay through a process of alpha or beta emission until they get to a very stable isotope. So here we're going to practice writing a nuclear chemical reaction for uranium-238 that undergoes alpha emission. So here we would write uranium-238 and then helium on the other side. And then we would try to find the element that adds up, that would help us to add up to 92. and that's thorium. Thorium-234. So the numbers all add up between the atomic masses. 4 plus 234 equals 238, and 2 plus 90. Okay, that was a short little detour here. What about predicting nuclear stability? Here are the steps to thinking through this process. First of all, you want to analyze what is the nuclide or the isotope mass versus the atomic mass on the periodic table, just what we did for that first question here today. If it's heavier, that isotope weighs more than the atomic mass on the periodic table. That means its N to Z ratio, neutron to proton ratio needs to decrease. And then we can predict that that isotope will emit an electron. So it means it will undergo beta or electron emission. If that isotope is lighter or the isotope weighs less than the atomic mass on the periodic table, then the neutron to proton ratio needs to increase, and it will use either electron capture or positron emission, and you can pick. It's one of those two things, and you pick. Now here's boron 8. What kind of emission or let's go with what kind of radioactive decay process would this undergo? So what we do is go, okay, boron 8, how do you compare to the mass that we see on the periodic table? Man, if I could look behind me and see what it is, that would be great on my screen. So I think boron is around 10-ish as for its average mass. Okay, so 8 is less than 10. So I would predict, since it would fall under the too light category. So we would tend to predict in this example then that boron 8 would decay by electron or positron emission or electron capture. Why? Because if it does that, it's going to now turn into beryllium 8. And beryllium 8 actually is going to have its proton to neutron ratio to be more similar. It's element 4. So that ends up having a more favorable, more stable proton to neutron or neutron to proton ratio. All right, let's go back to our example with cesium-137. What kind of decay would that one go under? Remember, 137 was heavier than the atomic mass. So we would predict what? All right, hopefully you picked beta emission, and that is correct. So based on this, what kind of element would result after cesium-137 undergoes 1 beta electron? Here are some options. See which one you can come up with. All right, hopefully you picked barium. As cesium gives off an electron there, we now know that the masses and charges need to add up. When I say charges, I mean the nuclear charges, the Z number there. So we end up with barium-137. Hopefully that's what you picked. All right, so we can do these kind of things and think through the process of which elements could undergo, and we can make these predictions. So based on nuclear stability, what is the symbol for the most likely product nuclide when phosphorus-28 undergoes decay? Write the reaction for this. So what are you going to do? Well, I'm going to figure out that mass relative to the mass on the periodic table. If it's too high, then I'm going to use, if it's heavier than it, then I'm just going to do beta emission. If it's too light, then I'm going to use positron emission or electron capture. They'll do the same. So this is true for the lighter elements less than 84. Anything heavier tends to decay by alpha particle. So what do you think? Well, here's how you would write it. Phosphorus-28 has an atomic number 15, and if it gives off that is lighter than phosphorus on the periodic table. Phosphorus on the periodic table has an average mass of 31, and 31 means that the average mass is heavier than the phosphorus-28. What we can gather from the atomic mass on the periodic table is that the average masses really kind of indicate where is stability. And so this is lighter than stability, so it's not really that stable. So As it converts into silicon-28, this then creates an element that's really close to something that's stable. So these are things that our students should start to think about, and how to write them, and go through this process. So I think I had one more. And so we'll end it on this one. Based on nuclear stability, it's a symbol for the most likely product nuclide when carbon-14 undergoes decay. Write a reaction for this. So I go look on the periodic table, and I see that carbon-14 ends up being heavier than carbon-12. 12 is the atomic mass. So that means if it's too heavy, then it'll need to undergo beta emission. So that means it's going to give off an electron and end up with nitrogen-14 as the answer. Well, hopefully you've learned a few new things about nuclear chemical reactions and radioactive particles that are given off, and how to write nuclear chemical reactions, and how to balance them on both sides. And hopefully a few new particles, a few new friends and faces out there for us. All right, I'm Dr. Ryan Hayes. Thanks for joining me. And if you have questions, contact me. Otherwise, have a great day, and keep your eyes open for all the amazing chemicals and chemical reactions that are taking place all around us. Take care.